Good morning, afternoon, good evening, everyone who joined, and maybe more people will join later as usual. So let me introduce our speaker today, which is Sophia Musho. And Sophia is a broadly educated astrophysicist who studied a lot of solar phenomena such as jets, flares, and coronal mass ejections. And now she's basically concentrated on applying this solar knowledge, solar luggage, to other stellar systems, finding similarities and differences between them. So her formal steps is Bachelor of Science in 2010 from University of Athens, Greece. Master of Science in 2 years after that, again University of Athens, and then PhD in 2016 in Leuven, Belgium. Now she's postdoctoral researcher in Howard Smithsonian Center for Astrophysics. Sophie, have I forgotten something significant about you?
Okay. No, I think that's all.
Okay, so if so, please go ahead and tell us about Helios physics as applied to stellar system. Again, I will interrupt only if needed to clarify something. Otherwise, you have 45 minutes in total with questions.
Okay.
Go ahead.
Thank you so much, Gregory, for introducing me and for inviting me to give a talk in this global forum. Greetings to everyone. I am very excited to give this talk. As Gregory said, I consider myself having a solar physicist background, but in the last 1.5 years at the Center for Astrophysics, I've been learning a lot of stellar physics as well. So I will be wearing both hats during this presentation. Here I'm showing a list of my main collaborators. So without further ado, I will begin this presentation with a motivation why as solar physicists we should jump into the astrophysics field at the moment and what we could learn as a feedback from this process. I will talk about solar and stellar magnetic fields and activity cycles, and the structure of the heliosphere and its size, and also I will discuss what we know currently about astrospheres. Next, I will talk about solar and extrasolar space weather. This is a part where I'm particularly interested in. And I will finish with future missions and takeaway messages. So there are currently more than 3,500 confirmed exoplanetary discoveries, most of which are due to the Kepler mission. So we have discovered planets throughout different scales, from terrestrial planets up all the way up to gas giants such as Jupiter. This has created naturally the need for characterizing these exoplanetary environments. But as solar and space physicists, we know a thing or two about habitability. This is because we have an entire fleet of satellites taking high resolution and high cadence observations throughout the almost throughout the entire heliosphere. And we have been observing the sun almost throughout the entire electromagnetic spectrum for decades already. So the question really comes down to whether we can really generalize all this knowledge that we have accumulated of detailed processes in the sun in other stellar systems. As an introduction, the stellar classification currently in astrophysics includes 7 different types of stars, starting with O stars that are the most massive, that appear most blue, and warmer stars, all the way down to B, A, F, G, K, and M stars that are the smallest stars in the universe, that appear more red and are cooler in general. Our own sun is a G-type star, And M dwarfs, because of the fact that they make up to 70% of all stars in our galaxy, have a special importance. And then when we try to apply this in stellar astrophysics, can we learn something in terms of fundamental physics as solar physics and space physicists? On one hand, in solar physics, we have continuous high-resolution, high-cadence, and multi-wavelength and in-situ observations in the interplanetary environment. Thus, our models are very constrained, and we have been able to develop very sophisticated physical models. However, we only have information about only one star, our Sun. On the other hand, in stellar astrophysics, the community has statistical information on many different stars of different spectral types, and there are models that are taking into account also stellar evolution, how stars evolve from the moment that they are born onward. Recent exoplanetary discoveries have brought a new attention, a new light in the stellar physics field. But however, we only have very limited information about specific parameters such as stellar winds and interplanetary environments at hand currently. So this has led to models being pretty unconstrained. So the question comes down to how can we bridge the gap between the two communities. I will start discussing solar and stellar activity. Giant high-mass stars first have a convective zone and then a radiative envelope outwards. When we go to sun-like stars that are a little smaller, they have first a radiative zone and then a convective envelope as their, let's say, outer layer. And then very low-mass stars are fully convective. Now, the interesting part is that since the convective layers in sun-like and dwarf stars is the outer layer in the structure, they both drive magnetically driven winds. They both have magnetically driven winds. We have been studying the solar activity for a long time already, and specifically for the sunspot numbers, we have been taking observations for centuries. We have centuries worth of data. We know that sunspots start forming at middle latitudes in both hemispheres, and they gradually migrate towards the equator, where magnetic flux cancellation takes place. However, the sunspot number is not the only quantity that varies through a solar activity cycle in the sun, but in particular, and of special interest is the X-ray flaring rate and also the solar radio flux that also follow the sunspot variation. X-rays and radio are considered good activity indicators, not only for the sun, but also for different stars. For the sun, we have fantastic observations. For the sun, we have great magnetic field observations. However, for stellar magnetic fields, we can obtain the stellar magnetic fields either through using flux transport models and scaling the solar magnetic field by a factor, for example, 30, as I'm showing in this particular figure, or we can use direct measurements. Very commonly, broadly used technique is the ZDI, or Zeeman Doppler imaging technique, which uses Doppler imaging to map the sunspots on the surface of the star, and then it uses Zeeman broadening and polarization to measure the strength and the polarity and the direction of the magnetic field. Thus, at the end, we're able to construct the full, low resolution though, magnetic map of the large-scale magnetic fields in different kinds of stars. There are different groups that have been working with this kind of observations, ZDI observations. All our knowledge about stellar magnetic fields through the ZDI can be gathered in a figure like this, which rightfully so has the name of a confusiogram, because it has condensed a maximum amount of information. Notice that the sun lies on the top right corner, and it has on the vertical axis one solar mass, of course, and a rotation period on the horizontal axis of about 27 days. I want you to focus your attention on the lower left side, where M-dwarf stars live that are active stars and fast rotators, and also the size of their symbols here indicates that they have very strong magnetic fields of the orders of a few kilogauss. Now, dynamo simulations are able to reproduce these large-scale magnetic fields of the order of 3 kilogauss, but not only that, it also provides us a glimpse into the fine-scale magnetic flux distribution in these kinds of systems. So this can provide us some, let's say, more theoretical understanding of how the magnetic field field flux is distributed in smaller scales that we cannot get otherwise from ZDI imaging, for example. The Sun is not the only star that has that is showing an activity cycle. For example, Iota Orologium is the star with the shortest known activity cycle. This star has been under monitoring for more than 15 years now from different campaigns, which have verified that it has indeed such a short activity cycle. These campaigns have been monitoring the chromospheric activity through their measurements. If you want to know more about it, you can read Alvarado Gomez et al. That was published earlier this year. Now, dynamo models have also been able to reproduce activity cycles. For example, for a star with strong magnetic fields of about a couple kilogauss, such as Proxima Centauri, and a slow rotation period of about 80 days. Yadav et al. 2016 were able to reproduce a 9-year cycle, which is consistent with observations that observe a 7-year activity cycle. They were able also to reproduce the magnetic field flipping from one part of the cycle to the other, as you can see in the middle and lower panels with red and blue, as are magnetic field different polarities and extend all the way from in between the two poles. Now let's move to the heliosphere and astrosphere, see what we know there. The solar wind, from the time that it leaves the sun and propagating away, it accelerates until it reaches the Alfvén speed at the Alfvén surface, which is located at about 1.1 AU away from the sun, about 20 solar radii away from the sun. After that, it continues as with superalfvénic speeds. The solar system planets live most of their time in this superalfvénic regime with the Earth, forming a bow shock where the solar wind meets the magnetospheric material, and we have a magnetotail at the opposite side. However, every few years, for a few hours or so, the Earth experiences subalfvénic conditions. Then this causes the magnetotail to open up and create two different Alfvén wings. After normality is being restored after a few hours or so, the Alfvén wings, they come back together and they form the magnetotail again when we live in the superalfvénic regime. The solar wind continues at superalfvénic speeds up to the termination shock, where it becomes subalfvénic sharply. The next layer of our heliosphere is called heliosheath, and this is where plasma becomes more dense, the magnetic fields become more turbulent, and the solar wind essentially spins down until it meets the very outer layer of our heliosphere, which is called the heliopause. And this is where the interstellar medium and the solar wind interact, and their pressures counterbalance each other. So the wind completely stops. It has a V equals 0. The extent of our heliosphere is on the order of about 100 AU or so. Outside of our heliopause, there is a neutral hydrogen wall forming, and this is a structure, a large-scale structure, as you can see in the figure, that can be observable through Lyman alpha observations. And indeed, we have seen different astrospheres using Lyman alpha observations. We've seen different astrospheres of different sizes and shapes for a few stars already, and mainly through the Hubble Space Telescope. By studying this neutral hydrogen wall in Lyman alpha, we can gain some understanding about the winds that the particular stars observed are driving. So, Brian Wood has been making these observations for a few years already, and he has gathered a nice data set. This is a figure of his paper that was today, his refereed proceedings paper that was published today in AstroPH. We can see in this graph I'm showing the mass loss with X-ray luminosity at the horizontal axis, and they are both normalized with respect to the surface of the particular star. The Sun lies at the vertical axis 1, has a mass loss of 1 in solar units, and it has an X-ray flux of about 10 to the 4. The X-ray activity, as we said, the X-rays are an activity indicator. So less active stars than the Sun lie to the left of this diagram, with more active stars lying to the right part of the diagram. So we see that more active stars than the Sun drive more massive winds. They have a larger mass loss rate, up to 100 times more than the Sun. However, once we reach an X-ray activity threshold, we see that this trend stops suddenly, and more active X-ray active stars appear to drive weaker winds at this regime. Now, astrospheric dynamics depend on the age of the star, the rotation period of the star, the stellar activity, as well as its magnetic fields, which we will address one by one later on. This is a diagram where I'm showing the fractional X-ray luminosity with respect to the total bolometric luminosity of a star as a function of the Rossby number, which is essentially the ratio between the rotation period, the characteristic convection turnover time. We see that the Sun lies at the bottom right corner, and faster rotators lie to the left. The faster rotating a star is, it appears more X-ray active until we reach a particular threshold, which is close to 0.1 Rossby number of 0.1. Then, even faster rotators than this regime don't appear more X-ray active. So this is called the saturation regime. This diagram is a good approximation for stellar dynamo. We see here that FGK stars are indicated with gray circles, and with red filled circles are the M dwarfs. We see that both types of stars, both the M dwarfs and the rest of the late type stars, they all lie in the same trend, which means that both fully convective stars that are M dwarfs and partially convective stars that are FGK stars, they have similar dynamo behavior. So a star, however, from the moment it's born, it's a more fast rotating stellar system, and gradually it loses angular momentum and spins down, as for example the figure indicated, the video indicated. This is through a mechanism that is called magnetic braking. And the mechanical analog of this mechanism is a ballerina, that is a figure skating artist, that is spinning around, and she extends her arms in order to spin down more efficiently. Open cluster observations have been are very useful in astrophysics in general, because it gives us the opportunity to study a collection of stars at the same age. Open cluster observations have indicated that the rotation period with respect to the spectral type is a bimodal distribution. That is, we have a slow rotating branch indicated by the red top line, and a fast rotating branch, which is the lower green line, and a sparsely populated region in between. Skuman et al. In 1972 modeled the slow rotating upper branch as square root of the age of the cluster. We see that as ages of the cluster progress from left to right, stars start moving from the fast rotating branch to the slow rotating branch by spinning down, passing through the intermediate region until finally we have no fast rotating stars in our cluster. The stars that live the longest in the fast rotating branch are M dwarfs. There have been several efforts to try and reproduce this bimodality of the rotation period distribution, but also understand the mechanics behind the magnetic braking. However, a breakthrough took place 3 years ago when Garafo et al., using the state-of-the-art code VATSARA, sustained by the University of Michigan, were able to include magnetic complexity into this magnetic braking mechanism. This essentially says the following: the more simple the magnetic field, the more like a dipolar magnetic field is, the more open magnetic field topologies we have. And this leads to very efficient spinning down. Whereas when we store magnetic flux in higher moments, that is when we close essentially our magnetic field topology, these kinds of stars, they stay for longer, being faster rotators because they don't extend their arms, their open magnetic field topology. Now, including an evolving complexity in their models, as well as taking into account the magnetic braking, Garafo et al. Earlier this year were able to reproduce the simulations in blue, to capture in the simulations in blue the observational trends which are indicated in red. The different panels show different ages of the open clusters. More specifically, the authors were able to reproduce both the slow rotating upper branch and the fast rotating lower branch, as well as the migration from the one to the other, also accounting for the fact that M dwarfs will stay for a longer time in the fast rotating branch. Now let's move to solar and stellar environments. Stellar environments can be affected by stellar winds, coronal mass ejections, flares, energetic particles, but also, especially in some active stars, by high energy radiation. We will discuss all these points. Let's start though by following the energy. Each particular active region on the Sun or other stars has a specific amount of magnetic energy available to then be distributed, that can then be distributed between CMEs, flares, energetic particles, heating, etc. At the very center of the CME flare scenario lies the magnetic reconnection, which is a process that takes place at the top of a magnetic loop configuration in the solar corona. Then accelerated particles start moving toward the Sun and interact with magnetic fields and plasma of the solar atmosphere, and they are emitting radiation almost throughout the entire electromagnetic spectrum, ranging from X-rays all the way down to radio frequencies. So flares are very multi-frequency bursts. In the solar regime, both flares and CMEs can and have been fantastically imaged and resolved for decades already, and in particular our EUV observatories have allowed us to gain a lot of information on even at the very small scale dynamics that take place throughout the entire atmospheric levels of the Sun. CME shock waves have a very characteristic radio signature. They are associated with type 2 radio bursts. Type 2 radio bursts have a very characteristic frequency drift at the dynamic spectrum. That is, when we stack frequencies with time, we see that the peak frequency is drifting. And this is due to the fact that CME, as it propagates outwards, it expands, so its material becomes less and less dense. That's the frequency drift. There has been, with respect to the X-ray flares and CMEs, there has been a bunch of statistical studies for the solar case that have associated the flaring X-ray energy on the horizontal axis with CME mass on the top panel and kinetic energy on the bottom panel. A very clear trend was revealed. More energetic flares are associated with more massive and faster CMEs. Then, from the fantastic statistics that we have from the solar physics, we are able to figure out the distribution of flares per unit energy and can eventually figure out the energy and mass loss rates as a function of the X-ray luminosity of the sun, and then we could scale the energy and mass loss rates as a function of X-ray luminosity, for example, for more active stars. So I'm showing here the mass loss with respect to the X-ray luminosity and the kinetic energy loss with respect to the X-ray luminosity at the first lower left side of the panel. At 10 to the 27 ergs per second is the current X-ray luminosity of the current day sun, and it corresponds to a mass loss of the 10 to the minus 16 solar masses per year. This is a reasonable value. However, once we extend all the way to the high energy regime, and we go to a few 10 to the 30 ergs per second, this is a young sun analog type of star, and this has a mass loss rate of about 10 to the minus 10, a few 10 to the minus 10. Now, if we assume that this star stays with this mass loss rate for about 1 billion years, then we take that this particular active star, a young sun analog, could lose a few % of its entire mass through CMEs. This is actually a good thing because this can explain the famed young sun paradox, which says that if the sun would be of a similar mass as it is today, and with a similar mass loss rate, then it would be too cold for life to form on Earth as we know it. Whereas if it were bigger, it would be hot enough for life to start, and then it would lose mass with a faster rate when it was more active. However, and this was verified by Arneo et al. For T Tauri young stars. However, when we move to the energy and we move all the way up to the high energy regime again, we see that the solar extrapolation for more active stars gives us that CMEs could strip away 10% of the X-ray luminosity of the star in that way. We know, however, that the dynamo essentially mechanism cannot extract such a high energy fraction out of the star through CMEs. So we have an energy problem there. CMEs can be good thieves of energy from the stars, but not that good. Now moving to energetic particles. We know for solar energetic particles have been studied majorly for the last few decades, and we know that they can be accelerated at CME shocks, and these solar energetic particle events are characterized as gradual. They have a gradual X-ray behavior. They can last up to a few days, and they're associated, as we talked about earlier, with type 2 radio bursts with a characteristic frequency drift. Solar energetic particles can also be accelerated at flares. These events are more impulsive, and they have an impulsive X-ray behavior. They can last up to a few hours, and they are associated with type 3 radio bursts that are indicators of electron beams. Now, understanding particles, the energetic particles in protoplanetary disks, and in general understanding protoplanetary disks is a very important task because this is where the planets are born. Protoplanetary disks are still around young stars that are still accreting mass and losing angular momentum. The dynamics of protoplanetary disks, however, are very complicated because they consist of weakly ionized gas, which is dominated by non-ideal processes. The main point in this kind of studies is the ionization, and to see which process governs the ionization in which parts of the disk. It could be either X-rays or energetic particles. You can learn more about it on the paper published earlier by Francetti, 2018. Another thing I would like to point out is that protoplanetary disks are humongous structures, almost on the scale of the heliosphere, about 100 AU or so, and we can image their different parts in different frequencies, starting for high frequencies in the UV continuum very close to the star, to the main star, and moving to lower frequencies all the way out up to sub-millimeter frequencies. But we started this discussion because of the habitability issues around active stars. Let's start by defining the habitable zone. The habitable zone is essentially the distance around the region around the star where planets can host liquid water around in the surfaces. For the case of the Sun, this habitable zone indicated in grid is between 1 and 2 AUs. Hooray, we live in the habitable zone, good for us. However, for cooler stars such as M dwarfs on the lower part, we see that all this green habitable zone is moving all the way very close to the star. This can have several very important implications. For example, the M dwarf TRAPPIST-1 system has 7 terrestrial-like planets that are all crammed in a region much closer, for example, when we compare it to our solar system structure, much closer than the orbit of Mercury. 7 planets, much closer to the star than the orbit of Mercury in our own solar system. Let's start with stellar winds. Garafo et al. Last year simulated the wind of TRAPPIST-1 using an average large-scale magnetic field of about 600 Gauss. They used the state-of-the-art Batcharas code and the OSAM model, which is using Alfvén wave heating to drive the wind. Here there is a slice along the ecliptic plane. With white is shown the Alfvén surface, and we see the different colored orbits that they cross the Alfvén surface twice during their orbit. Most of the time, most of the orbits, they live in the subalfvénic regime around TRAPPIST-1, and they cross briefly during their very short orbital periods of the order of a few days. More specifically, here I'm showing the pressure that the stellar pressure that these different planets experience, normalized with respect to the solar wind pressure at the orbit of the Earth. So we see that for all the TRAPPIST planets, all TRAPPIST planets experience 1,000 to 1 million times more intense pressures than the Earth does for normal conditions. And also, on top of that, they also experience about an order of magnitude fluctuations throughout their orbits that last only for a few days as they cross the Alfvén surface from the sub to the superalfvénic regime and again back. This is a simulation of one of the outermost planets in the TRAPPIST-1 system, and we see that as it lives most of the time in the subalfvénic regime, it doesn't have a tail but rather Alfvén wings. And as it crosses, and it's trying, if you notice in the video, as it crosses to the superalfvénic regime, it tries to form a bow shock and a tail, but it doesn't have enough time to relax in this state, and then it opens back again to the Alfvén wing structure. This can be an overwhelming conditions for the atmosphere of this planet. So what about energetic particles on top of this simulation? Francetti et al. Is working on simulations of using the stellar wind simulation of Garafo et al. To study how the energetic particles will affect the planets in their different orbits. He starts by injecting a collection of particles at a specific distance from the star, about 10 stellar radii, for example, and sees how many and at what distribution particles reach at the orbital plane of these different planets, assuming turbulence, assuming a value for the turbulence. For example, for the TRAPPIST-1b, the first planet in the system, and with a small turbulence, we see that the energetic particle distribution is rather uniform, especially around the equatorial plane, around 90 degrees or so. On the other hand, when we assume at the lower right panel a more moderate value of turbulence, we see that this uniformity breaks down immediately, and the planet experiences much more intense conditions in one part of its orbit than in its other. And this is all happening in a very short amount of time. This can have devastating consequences and lead to atmospheric escape. On top of that, since these planets are super close to these active stars, they experience more X-ray and ultraviolet high-energy emissions. This can lead to ionization, energization, and escape of their atmospheres. Atmospheric escape has been observed in exoplanets, in exoplanetary systems through Lyman alpha observations. Now let's move though to stellar flares, which are my special interest. Well, what do we know for stellar flares? So when we point our, for example, X-ray telescopes towards an active M dwarf, we see that it flares all the time. We point it for a few hours and we take one flare after the other. But this doesn't only happen for active stars, but also sun-like stars. We have observed more than, the community has observed more super flares with energies more than 10 to the 33, as is shown with the colorful points in the upper right panel. For sun-like stars, these are called super flares because they have energies more than the most energetic solar events that lie on the lower left side of this panel. We have also seen several stellar flares for decades already, since decades already in radio. So we've seen stellar flares wherever we look at from one side of the spectrum to the other. However, for stellar CMEs, we are not that lucky. We cannot image them directly, since most stars are just point sources from where we stand. But there are other indirect stellar CME observations that we can take advantage of. The first one is through Doppler shifts, mainly in Balmer lines such as H-alpha that are looking at chromospheric material, but we can measure Doppler shifts in, for example, X-rays as well. Here I'm showing an example of 2016 with the CME signature in the blue side of this diagram, where the observers measured a 600 km/s speed, which is an outflow speed larger than the local escaping velocity. So this is escaping velocity in Doppler shifts. Another way to observe stellar CMEs is through X-ray absorption. Here I'm showing one of the most extreme flares ever observed, the Algol super flare, reaching energies 10 to the 37 ergs. And at the same time, just a little bit after the peak of the flaring energy, we saw a significant increase in the column density, which I remind you is indicating that suddenly material is blocking our line of sight for the flaring site. And then there was a decay phase for the column density that lasted for about 14 hours or so in this case. CME expansion is consistent with the particular decay of this event as t to the because it drops as t to the -2 is consistent with the self-similar expansion. And then we used the geometric CME cone model that's majorly used in solar physics in order to estimate the CME kinetic energy and mass, and we published this work in a paper last year. We also gathered a few of the CME candidates currently available from historic observations, and our preliminary results indicate the stellar, here I'm showing the stellar events with green, the solar events with gray, and some historic solar energetic events with white and the Carrington event with orange. We see here that given the spread of the solar values as well as the large error bars of the stellar events, we see that, for example, for the mass, the stellar events are lying in the extended solar trends. However, for the kinetic energy, we see that also given that we have our very small sample for the stellar events, we see that there is a kinetic energy plateau that starts forming after some energy, and this is due to the fact that there is only so much energy available in a system for a CME to strip out of it. As we said, CMEs are good strips of energy, but not that good. They cannot exterminate the full star with one go. A very...
Okay, 5 minutes.
There's another type of promising observational technique that's tied to radio bursts, as we said, with a characteristic frequency drift, using, for example, facilities such as the VLA to make surveys. However, there's no detection yet available. You can read more on the Crossley 3 papers if you're interested to learn more about the non-detection events. However, simulations could be the savior in this situation. We are very proud for our simulations and our paper that is currently under review, that we are simulating towards a realistic radio corona. We have used the state-of-the-art Bacharas code and the OSAMAR model, and on top of it we have implemented the radiosynthetic imaging tool and consistently incorporate Bremsstrahlung refraction. These are our results, and we have compared at both low and high frequency, and they agree with observations at first order. We see that in low frequencies, the disk appears as an extended fuzzy ball image structure, but then as we move to higher frequencies, to the left and to the bottom, up to 10 gigahertz, the higher frequencies are able to penetrate deeper in the solar atmosphere, and they thus have access to stronger magnetic fields, and they refine smaller scale structures with stronger magnetic fields, such as the active regions. For the CME structure, we have shown that we have a qualitative agreement with observations, and we have a more intense CME. The CME is more intense, closer to the sun, contrary to the bubble-like structure at the rest of it. Now, another potential method for observing the stellar CMEs is through EUV dimming, by quantifying how much the CME, by leaving the star, evacuates its atmosphere from material. However, no stellar detection has yet taken place either here. So to wrap up, we need to really move beyond the purely temperature-based habitable zone definition, and we need to account for extrasolar space weather, and in particular for CMEs and flares. We've seen that monster CMEs are expected from solar extrapolations associated with the super flares that we already have observed. However, we are not nearly close to observing as many CMEs as the bunch of flares we have seen already. And the question comes down to whether this is purely due to an observational bias, or there is a fundamental process that is actually suppressing the CMEs. We need more observations and theoretical modeling to understand this. On that note, Drake et al. Are working on a theoretical analytic model on CME suppression. They're showing the kinetic energy on the vertical axis as a function, the kinetic energy of the CME as a function of the magnetic field, the equatorial magnetic field of a particular star. We see for solar values 1 to 10 Gauss that the range of the solar CMEs is reproduced 10 to the 28 to about 10 to the 33 ergs. And interestingly enough, also so is the lower solar limit. So below 1, we don't have CMEs with energies 10 to the 26 ergs, for example. Then once we move to the more active star regimes with magnetic fields more than 100 Gauss, we see that this threshold moves to very high energies, 10 to the 34, 10 to the 35, for example, for 1000 Gauss. So only monstrous events would escape. This was then tested with a computational experiment by Alvarado et al. 2018 early this year. They used a large-scale magnetic field of about 100 Gauss on top of a solar magnetogram, and then started with the CME having a low poloidal flux. The first experiments did not escape, and they kept increasing the poloidal flux until some of the CMEs were strong enough and so that they were able to break through the strong overlying magnetic field. To summarize the results, using statistics from the sun, they were able to come up with the threshold that the kinetic energy of the CME needs to be at least twice as high as the entire flaring energy of the associated flare in the entire electromagnetic spectrum. We see here the red are the confined 6 confined events and 6 escaping events in blue. If you look at the upper horizontal bar, you see that all the solar range events are suppressed with an overlying large-scale 100 Gauss magnetic field, and only very energetic events with X100 to X1000 are able to escape. Now I will finish with discussing a few future mission capabilities. In the radio observations alone, we are expecting for the square kilometer array that will focus on protoplanetary disks and will join the search for extraterrestrial intelligence. A very exciting mission is Sunrise, which will be a solar space interferometer and will consist of 6 spacecraft. It will focus on very low frequency transient events. NGVLA, we're expecting to get really high quality stellar observations from this from its future capabilities, and even Parker Solar Probe and Solar Orbiter, even though their main focus is different, they both have remote sensing radio capabilities. Finally, the Hubble Space Telescope will continue observing astrospheres until at some point it will be replaced by the James Webb Space Telescope. The Transiting Exoplanet Survey satellite test is already for a few months now taking observations since earlier this year. LYNX is a very exciting mission that will eventually, we're hopeful that will eventually replace Chandra, and this will give us a glimpse, a very good idea of what happens in small-scale dynamics relevant to reconnection flares and CMEs. Finally, I would like to conclude by saying that sun-like and fully convective stars are both having magnetically driven winds. As solar physicists, the first thing that we can do is the first step we can take is to make extrapolations, and we can learn a lot by this alone, but we should not stop there. We need to consider stellar evolution and different types of stars and how to apply our models in them. And especially, we need to, since M dwarfs are 70% of the stars in the galaxy, we need to account for subalvenic and very intense activity regimes. As a takeaway message, I would like to say that there is a clear increasing interest for exoplanetary environment characterization, and as solar physicists, we have in our hands very sophisticated, very detailed models that we've been using for years in the solar and space weather regime, and we should definitely try to apply them in stellar systems, but take a step back and see how fundamental our models are. These are exciting times, and I think we should intensify our dialogue with our stellar peers. Thank you, William, for your attention.
Okay, thank you very much, Sophie, for your very interesting and exciting presentation. Now I wonder if anyone has questions. You can just unmute and ask. We have a manageable group of people to do so. Mm-hmm. Yeah. So by now all microphones are muted. This gives me an opportunity to ask questions which is within my field of interest about radio. When you mentioned that you simulated radio emission with Bachelor's code, you included refraction. I assume that this is refraction in the 3D volume.
Yes.
Described within the same model, yeah? And I have two questions. First, how important, how large are distortions related to diffraction? And the other one, do you include at all scattering by fluctuations or not? Yeah.
So thanks a lot for your question, Gregory. That's a very to-the-point question. Refraction is calculated through an iterative algorithm, and it essentially is calculating the refraction index at each different layer of the atmosphere. And it calculates the gradient of the density as we move towards the sun. And then at some point, we have a surface that depends on the particular observing frequency or synthetic frequency for us, below which this particular frequency cannot penetrate. So we take this pretty consistently into account in our code. As we can see in the results in these 6 panels, we see that we are able to qualitatively reproduce the size and the structures that we expect from low frequencies to high frequencies, how the solar disk is expected to appear. So in that sense, refraction is important in lower frequencies. However, for the moment, we are not really accounting for scattering, which, as very well you pointed out, this particular mechanism we expect especially at the very low frequencies, where, for example, sunrise will observe below 100 megahertz or so, that scattering will most probably take over. We are very proud of this particular modeling and synthetic effort, and we are aiming at including scattering, and also not just bremsstrahlung, free emission, but also include plasma, gyrosynchrotron, and plasma emission mechanisms that are more burst-like related.
Okay, thank you. Other questions?
I have a question.
Go ahead. Hugh Hudson.
Yeah, this is Hugh. The Vatsaras is an MHD code, and these simulations have to have particles added to produce this 10 gigahertz emission. How do you estimate the particle numbers?
I couldn't hear you very well. I didn't hear the last part. Which was the question?
The question is about the particle populations of non-thermal particles to produce the 10 gigahertz emission in your simulation. How do you estimate the particle numbers?
Okay, so this particular simulation, that's a very good comment as well. This is purely an MHD simulation, as you pointed out. We have like a 2-temperature model that was published in 2014 by Van der Holst, etc. But it's essentially an MHD code, as you said. So we don't really account for the specific particles. Our computation is solely for the free bremsstrahlung emission. It solely depends on the pressure and the pressure gradient in the different parts of our 3-dimensional domain, computational domain. So we just use the MHD density to calculate the refraction on top of this. Of course, this is a large-scale project, and we are really, this is my main focus of my work, to account for both kinetic and MHD dynamics more consistently using either semi-empirical models that already exist in Vatsaras, or even better, doing particle and cell simulations or hybrid simulations to take into account both kinetic and large-scale physics.
Hugh, any follow-up? So?
No, that sounds good.
So basically, next step, when you will model plasma emission and other kinds of georesonance, geosynchrotron stuff, will require assumptions or models for thermal.
Absolutely,
yeah.
Absolutely. You're very right. I'm very excited to do this steps. However, it's a very large-scale project, and as you know, with the simulations, it takes some time to implement everything and test everything.
Mm-hmm. Other questions? Okay, I see that all microphones are muted. So if so, let me thank Sophia again for interesting talk, and let me close the webinar. Next one will take place in 2 weeks from now. So thank you very much. See you then.
Bye-bye. Bye-bye.